Okay, so a little derivation relating to the ideal gas law. So the ideal gas law, of course, says PV is nRT, but we want to try and understand um, where the pressure comes from. So if we think about the atomic scale, the pressure is actually coming from the molecules colliding with the walls of the container. So here's a gas molecule of mass m moving at a speed vx, and let's imagine it collides elastically with the wall of the container, bounces right back out at the same speed vx. So we can use the impulse momentum theorem to say that the force that will result is the mass times the acceleration, and the velocity change, because of the change in direction, is just twice vx. So if this is 3 and this is 3, that's not a change of 0. That's actually a change of 6 from a vector point of view. You know, these things are both vectors, but I won't bother with the vector sign. So there, and this happens over a time t. So that's an expression for the force of this one collision. But if there's n collisions, then the total force is just multiplied by n. So this is a microscopic or kinetic perspective. Now, if we imagine then a volume of gas here, there'll be a cylinder of gas that's going to collide with that wall in time t. And let's say that the cylinder has area A, and if this particle is moving at Vx, then the length of this cylinder, the atoms of gas that are going to collide with the wall in time t, is just their speed times time. So the volume of this cylinder then is cross-sectional area times the height. Now this area also appears in the definition of pressure, because pressure is collision force distributed over that area. Now, the number of particles that are actually in here, so the number of particles in this volume, which is A Vx t, will be the same as the total number of gas particles, and the total number of particles will be the number of moles times Avogadro's number, Na, which is 6.02 times 10 to the 23rd particles per mole. So this is the total number of particles of the gas, and this is the total volume of the gas. So we're finding the number of particles in this volume just using the ratio. We're saying that the density of particles and the distribution of particles is a constant, so the total number of particles in the total volume will equal the number of particles in the cylinder over the volume of the cylinder, very simply. So now within that volume, half are moving towards the wall and half are moving away, so we're going to introduce a factor of a half here for the number of collisions. So n is the number of collisions that the particles make, and that's going to be half of the particles in the volume, and half of the particles, if we take that previous result and we just cross multiply this term over and up here, then we get this result here. It's the number of moles times Avogadro's number times the cross-sectional area of our cylinder, the x velocity of the particles, the time of interest t, and then we divide by the gas volume V. That's the total gas volume. Now, within the gas, it's equally likely to have a particle moving in the x, y, and z direction. So we expect the average x, y, and z speeds to be equal to each other. So for the overall speed then, which is the sum of those three, each one of those is on average going to be the same. So we get a factor of root 3 times the x speed is the overall speed, or, because our derivation had a vx squared in it, we see that is 1/3 the average speed of the particle. So, for our pressure, which is going to be a collision force over an area, the collision force is the number of collisions times this expression here, which was from the very first page in our derivation. So that's just the mass times the change in velocity over time. That's the acceleration. Now we're going to divide by the area in front here. And now we've got to put in our expression for n, which was 1/2 number of moles, Avogadro's number, and then AVXT, the volume of our cylinder. And then we have to divide by the total volume of the gas, and then we have to divide by the cross-sectional area there. That was pressure is force over area. And then we're multiplying by this, 2mvxt. Now there's a lot of stuff that cancels there. The area of the cylinder disappears, that's a good thing. Time disappears, that's a good thing. Now we better be careful. This is volume and not velocity, so let me make it look a little different here, maybe. And, oh, and also the 2 disappears. Doom, doom, there we are. And so we get, for pressure then, we get, the only thing that survives is n, the number of moles, Avogadro's number, over the volume. That's a bit messy. Oh, sorry, going to have to pause this and clean that up. All right, and so it remains to substitute this result for x speed, replace it with the overall speed, and we get for the pressure of our ideal gas, oh my goodness, what's going on here? So we replace Vx squared with 1/3 V squared, and we get this term right here. Now, we see that we've got Avogadro's number here. We don't yet have, remember this is the ideal gas law, we don't have the ideal gas constant yet. So we introduced Boltzmann's constant, which is actually a ratio of the gas constant to Avogadro's number. And if you divide those two, then you get the correct value for Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin. So we rearrange there our statement for pressure. So we pull out n, the number of moles, and the volume V, and then we had Avogadro's number, which I'm going to write as this way, and clearly that's equivalent because R would cancel. And then there's a 1/3 mv squared. Now, this is the reciprocal of Boltzmann's constant times 1/3 mv squared. Well, this must be the temperature, because the ideal gas law is an experimental fact, so pressure's got to end up being nRT over the volume V. So that tells us that this quantity is related to temperature. Well, how could that be? Well, what is that quantity? Well, if we're saying that this is temperature, then we can say, let's start off like that. 1 over K, 1/3 mv squared is temperature. That tells us that 1/3 mv squared is kT, Boltzmann's constant, times the temperature, which we can rearrange and cross-multiply the 3 up, and then divide both sides by 1/2 to make it look like kinetic energy. So this tells us that the temperature of that ideal gas determines the kinetic energy of the ideal gas. 3/2 kT equals the kinetic energy. And then since kinetic energy depends on speed, that tells you that the temperature of the ideal gas determines how quickly the molecules are moving. Now, this is actually the average molecular speed. So the temperature determines the average speed. We'll see in our next class, there's actually a distribution of speeds. You don't have just one speed, you have a whole bunch. Now we see here that this is kinetic energy in joules. This side has to be joules as well. And that works out because, of course, K, Boltzmann's constant, is joules per Kelvin. Here, ignore this, sorry. That was in the wrong spot. Let's bring this down here. That looks a little better. So this is Boltzmann constant times temperature. That is an energy unit. So kT, it makes sense to say that 3/2 kT is a kinetic energy, at least dimensionally. That's dimensionally correct. Now, if we solve for the average speed, cancel off the 2, divide by m, so the average speed is related to the temperature in this way. So another result that emerges from this derivation has to do with the fact that if the average x and y and z speeds are all equal, so if we look at that statement that 3/2 kT equals the kinetic energy, the average kinetic energy of our ideal gas, we can write that in the following way. So here's 3/2 kT, written as the sum of 3 terms. And then that's going to equal 1/2 mv squared. But of course, I can write v squared as the sum of the square of its components. So I can write it in this way. And so we see that each of those energies, each of those degrees of freedom, contribute 1/2 kT to the total energy. So an independent rotation or vibrational mode of a molecule contributes 1/2 kT to the total internal energy. Now, if we deal with a monatomic ideal gas, then that molecule just has 3 things it can do. It can be moving in the x, the y, or the z direction. Therefore, the energy per molecule, the total, which is the same as the total energy divided by the total number of molecules, is just 1/2 kT for each of those degrees of freedom times the 3 degrees of freedom. So cross-multiplying, and then rearranging a little bit and remembering that K times Na is exactly the gas constant R, we get 3/2 nRT for the internal energy of an ideal monatomic gas. So this idea that each independent mode or each degree of freedom contributes 1/2 kT, this is known as the equipartition theorem, since it really tells us that every degree of freedom contributes equally to the total energy, or rather that the energy is equally partitioned over each degree of freedom. So we'll talk in class about how this would apply to a more complicated molecule, say perhaps a diatomic molecule like oxygen or hydrogen or nitrogen. And then also we'll look at solids, a model of 3-dimensional solids, and think about how many degrees of freedom that has. That's our pre-lecture for today.